What you need to know is that at this office we don't do any drawings. So we develop machines. To clarify this difference between the drawing and the machine, you would have to really oppose them. Drawing is always a system of reductions. Now the machine is exactly the opposite. So you would do a diagram, a conceptual diagram in the computer, and it starts extremely simple. So it doesn't start complex, but it starts with a very simple system. I'll explain later how it's built. And we put information in that system, and we put all the information in that system. So in a drawing, you have to work in a drawing on the staircase, for instance. You're only working here. If you work in a machine, you can work at this moment, at this point, at every point, and they all integrate their solutions and their influences in the system. You get a very complex outcome. So the machine, in our case, is something that combines perceptual interest, it combines action, so all the information of a plan, of routing, and structural analysis. So all this information that is networked goes into a form, but the form is not something that is sort of passively reacting to the information, but it deals with it. It's like an ear. You put in sound, and the ear responds with the whole brain and the whole body to that sound and makes the whole system move. I think that's an important distinction you have to make with a datascape, right? The datascape, you have a simple clay-like form, and there's data going in it, information, and it eats from the form, and actually the form is left over. Here we have a system that is not just built of lines, but these lines have character. They're built in character animation software. So the lines and the points share the same continuum. All the lines are made of points, control points. All the control points are connected with each other with springs. So this is the whole network. Now these look like straight lines, but they're actually dead curves because they're uninformed. So in this software, a straight line is nothing but a very, very badly informed curve. Everything is a curve. So when you put in information, and in this software that always works with forces, all these influences, all these forces that want to make form, that want to make shape and space, come in the system as forces. So you run this system in time, and you get different curves all related to each other. So it's not just these four curves, but the whole thing is part of a very complicated system of curves reacting to forces. And the force that goes in here goes in this point, let's say the first second, then the whole force, the reaction, the response of the system is divided and distributed all over the system. So this is not like space. With the additive drawing system, you would always work in a space. When you're there, you're not there. But here, it's a topological medium. So when you're here, you're also here a bit. And it's like a weather system. So it's not a passive datascape, but it is a very active concept of material. So the organization is diagrammatic. You build it in a certain sense, but the diagram itself is not only of lines, but the lines and the points share the same continuum. In a topological system, every curve would have been directed by control points. Control points have tangent. So this point with the springs are actually influence fields that have a direction. And all these directions are negotiated by the curve. So the curve is an outcome of all these points of information. For the project in Nantes that we were asked to do, we have a museum, which is this one. And we were asked to do a project to inhabit 250 paintings in a classical Beaux museum. So our analysis of the mechanistic diagram of behavior vis-a-vis the system of the Beaux Museum is this. So you would have the axis, and our diagram is built first on the whole system of the Beaux Museum. Now, the whole exhibition was divided in 4 groups, A, B, C, D, Monde Inventé, Invented Worlds, Connected Worlds, Vision Machine, and hallucinatory worlds. Now, these were meant to be placed here, 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 and here. So we built a machine that placed the forces in these 4 corners. Now, all the paintings and drawings in this sector were very small. They were like the drawings of Henri Michaud that were drawn under the influence of mescaline. So they were very beautiful hallucinatory images, and we thought it would be the best to have these images very, very close to the face. So you wouldn't look at the image, but you would have a very, very private relationship with the image. So we made a very small force, but the machine that distributed the force over the system of 8 lines would move very easily all over the surface. This one was the Invented Worlds, and that was mostly connected to surrealist images like the paintings of Tanguy, Max Ernst, Brauner, Matta. So, and they needed a lot of space. The very large images, you need a lot of space between you and the image. So that's a large force. But this one hardly ever. In the software that we used, we took the vortex force. The vortex force is a very important force in Hollywood because they make films like Twister with it. You can have all the cows and all the cars and all the people and all the houses flying around. You have great software for that. Well, it's the same that we used. So if we run this software in this system, so the system is lines that are made up of points, control points, and the number of points is very important because you get a certain curve out of this, and all the points are connected by springs. Now, if you have it run with the vortex forces, you get very complex behavior of this system. So, for instance, all the lines would curve, but it's not like being happy curves, right? So these double curves, and actually double curves, they would all relate to each other in different positions. Now, that's actually the most important feature of topology, is that it's not something that is very tectonic that's being messed up by forces, but it's actually something that gains information. Well, it gains information, it restructures itself. You can find a new, more complex diagram in time that is much more coherent and a much more coherent reading of the information that goes in than any other system. So actually, in our system that we got out of it, it's more something like this. So we would have double lines. So there would be regroupings. There would be splittings. So the whole system would be a division of the 16 lines over different nodes. And that was very interesting to us. So we needed a system that could lift this model, which is made out of a sort of meta rubber. I mean, it has lots of material properties. It is, of course, an organizational thing, and it's not really made of material yet, but it has a lot of material properties. So I would call it something like meta rubber, and we would like to find a way, we were trying to find a way to translate all this into something that is more structural. So the first promise I had to make when I was talking to the client in Nantes was that the atelier was very good at finishing structures, but not very good at doing very complex construction. So the first day I already had to say we do the whole thing in wood. So the closest to wood on this level for us would be paper. Now you're not looking at a model here. This is not a model in the sense of what we call a maquette. So that is trying to do the diagram that you have in a format as paper. This is actually a paper computer, and it's very close to, let's say, the chain modeling technique of Gaudi, where he calculated the curves with a material property. So the pins are very close to the points in the animation software. These are actually the control points. So if you have a strip of paper or of a certain thickness, this is actually the definition of a spline. The word spline comes from naval architecture, and in naval architecture it means a strip of wood or of metal, and they used in the 17th century already, they used weights to calculate the curve, to calculate the right curve, one-to-one of the ship. So we are here dealing with a paper computer. Now the pins are very close to the animation software, but our animation software didn't have paper clips. Because our structural principle became this. Suppose you would have two lines that would move toward each other, like this. For us, that would be a tendency to meet each other. That's how we read it. So we read this movement as a structural movement. So in the paper model, we said, okay, if you move towards each other, you split up. Come back. You split up in such a way that you meet the other one halfway, and you cross each other. Ergo, we have a paper clip, and you would connect and build a structural relationship. So this splitting, right, this splitting technique, and that finding of each other, that splitting up, that is sort of, it's actually a line that when it splits up, it becomes more surface. And when it becomes more surface, it goes from something that only orients in this direction to something that orients itself in this direction. Now that's exactly what the vortex does. Because if you start with a system that is only oriented in this direction, and you put the vortex in it, you get a twist of the curve. And this is all coordinated with the other curves. So you would introduce a sideways orientation in the whole system. So that's actually also a structural principle. Now this is a Gothic principle. You go out of the column, you split up the column, you split up the line, and you make surface out of it, and the surface becomes structural. You get a vault. So we have these surfaces that were splitting, right, on the floor level. They would twist up and meet each other in the air, so we were creating vaults. Gothic cross vaults. Now this is a very complex version of a Gothic structure, and not only that, it's horizontal, because in Gothic structure you would of course have the columns, and then the vault, and it would bend back, so you would have to bend the whole thing to get a Gothic church. So this we showed to our client and the engineer we worked with. And then sort of the project stopped for a second because the engineer thought, well, this is going to be very difficult. Because this is almost like tonnerre, working with wood, with bent wood, and trying to create gross faults. So what we actually did is have this system again, which is a tendency toward realization. We put it again in a tendency towards virtualization. So we need all these extra information meeting each other. We read all of this as surface. All of this as surface. So in between we would have surface here, which would be wooden beams, and we would have double curvature surface in between these parts. So it made it into a complex system of ruled surfaces that is flat surfaces that are twisted and bent in different directions in between, and vaults, double curvature in between these ruled surfaces. So this again was all again in the computer. So then we did another decision. Because you have to know the essence of this project is that it's a playful going back and forth between emergent systems that are creating form bottom up and top down systems that want to read form from the top down. So with the making of the surface, we again made this top-down decision where we gridded the whole structure. Now grid is a very sensible thing because when it's top-down, it means that you work with gravity. So in that sense, all the surfaces that we get out of it, we could just cut them. So from a very complex system, we worked from rubber to paper to wood in a very sort of methodological sense to work out of the organization towards a structure that you could actually occupy. So people, wood, and paintings are now sharing the same continuum. So when you now move through the whole exhibition, what is actually so interesting is that the content, the actual content of all the images that are related to hallucination, that radiate vertigo and hallucination, is now part of the architecture. So when you're walking here and you don't see any paintings, you still feel them with your knees. So you're seeing with your knees over here. So the whole content becomes materialized in a certain sense, that now the whole content of the paintings are everywhere. So that makes it completely different than any other setup or any other idea of a museum, where you would always have to walk around and lock in with your eyes onto a certain image or a certain color. Then you walk over and you say ah or oh. So now all this merging of forces, the Henri Michaud and the Paul Klee and the Finsterlin and the Kiesler, because there are also lots of architects in this exhibition, they all intercommunicate and interrelate with each other to create a structure. So now when you walk through the exhibition, and you're seeing not only with your knees and your feet, but you walk in, and all the paintings start curving with lines. So of course there's lots of paintings that are below, almost close to the ground, which are almost vertical, but the others go up and they twist and turn, and the whole time you have to involve your whole body to see. So there's no seeing that is disconnected from moving. Nothing sensory is disconnected from the motor, so you always would have to move to see, and you would have to see to move. So the perception and action, which is always being separated in architecture, in the plan idea and the elevation idea, is now sharing the same continuum. So all the people are just walking through, looking around, finding their way, and moving through the structure.